Hi, it's Mr. Mac, and today we're going to be looking at circular motion and going through some worked examples that tell you how to do the calculations.
Welcome to Mr. Mac's Physics channel. He can explain things really well and is a lot of fun to watch.
In our Year 12 Physics course, we're studying circular motion as part of the first module, Advanced Mechanics. And you can see from the picture, this is a ride that goes round and round. We'll start to look at the physics of circular motion. So we're learning to describe and analyze qualitatively and quantitatively circular motion, and we'll be able to solve complex questions for objects executing uniform circular motion in a variety of situations. The New South Wales Education Standards Authority has these content outcomes. As you can see, there are 5 dot points, but within each one there are some sub dot points or dash points and some new formulae and some new ideas that we're going to learn in circular motion. So let's start with our worked example 1 on centripetal acceleration. Chris is on a ride at the school's Spring Fete. Her chair moves in a circle with a radius of 3.5 meters at a speed of 10 meters per second. The question is, what is her centripetal acceleration? Now, the first step in any calculation question is data. So v equals 10 meters per second and r equals 3.5 meters are both given in the question. The next step is to write down the formula from the formula sheet that we're going to use. And here it is, AC, centripetal acceleration, equals v squared on r. The next step is to substitute, and we do this mechanically, so we're not trying to calculate in our head. So AC equals 10 squared on 3.5. And then we calculate. And it might be that your calculator gives so many decimal places that it's just unreasonable. So we need to round them. And in this case, it's 28.6 meters per second squared, correct to 3 significant figures towards the center of the circle. Now in our second work example, Chris is on the same ride at the same school's Spring Fete with the same speed. Her mass is 65 kilograms. And the question is, what is the net force applied to her? So as with all calculation questions, the first step is data. We know v equals 10 meters per second from worked example 1. We know the radius is 3.5 meters. That hasn't changed. Her mass is given in this question as 65 kilograms. And we've already calculated that the centripetal acceleration is 28.6 meters per second squared. So we use a formula, good old Newton's second law of motion, F equals ma. Note there are vectors in this equation, symbolized by the arrows. And we substitute. This time we want to find only the magnitude, so we'll substitute 65 for her mass, 28.6 for the acceleration, multiply them to get 1,860 newtons, correct to 3 significant figures, towards the center. The centripetal force is not something that just mysteriously appears whenever things go in a circle, but it's a special form of the net force. So if you look at the picture, what is pulling on each of those chairs that a person is in is the tension in the chain holding the chair, and that's at an angle, and also the weight downwards due to the person in the chair. We cannot physically see or find a force that points to the center, but it's the resultant force of those two, the tension and the weight. In our third worked example, we're going to be looking at angular speed, and Chris again is on this same ride at the same school, at the same Spring Fete, the same speed. The question is, what is her angular speed? First step, data. So we know that v equals 10 meters per second and the radius is 3.5 meters. That hasn't changed. Omega equals v on r is the formula that we need to use. So it's simply a matter of substituting 10 divided by 3.5 to find 3.86 radians per second, correct to 3 significant figures. In worked example 4, we're looking at angular displacement. Again, Chris is on the same ride, going at the same speed round in a circle, and we're told that the ride lasts for 3 minutes. And the question is, what is her angular displacement delta theta? First step, data. We know V, we know R. This time we have the ride lasting for 3 minutes, which is 180 seconds in SI units. Here's the formula. Omega equals delta theta over T. So delta theta, just rearranging, multiplying by T, will give us omega times T, and we substitute. 2.86 we've already found, and 180 is in this question. When we multiply that, we get a very large number, 514.2857, and so on. Of course, we round that to 3 significant figures, which is 514 radians. But what does that mean? It means that Chris has gone around and around and around about 82 times in 3 minutes. It's a very fast ride. We'll work to example 5. Look at the diagram where we have a mass connected via a string, might be a nylon string, through a glass tube so that we reduce friction, and it's tethered to a ball. So the apparatus in the diagram shows the centripetal force consists of a tethered mass, M1, swung in a horizontal circle by a lightweight string which passes through a vertical glass tube to a counterweight, M2. Now, if M1 is a mass of 1 kilogram spinning in a circle of radius 1 meter, and the hanging mass is 4 kilograms, the question is, what's the angular velocity in revolutions per minute? Assuming neither mass is moving vertically and there is minimal friction between the string and the tube. So in this tethered mass question, we're told that we've got two forces that are balancing. The weight of mass 2 balances with the centripetal force as M1 goes around in a circle. So here's the data. Fc, the force to the center of the circle, equals Fg, the force due to gravity. M1 we're told is 1 kilogram, M2 is 4 kilograms, and the radius of the circle is 1 meter. And we need to find omega, the angular velocity. Here's the first equation, which is just equating the two forces. We know Fc is mv squared on r, or in this case we've got m1 v squared on r, and the weight is m2g. Now please note, we also know that the velocity equals r times omega. So if we replace velocity on the left hand side with r times omega, then we get m1r omega squared equals m2g. Rearranging and taking the square root, we find that omega equals the positive square root of m2g over m1r. Now we'll substitute the numbers that we have. We have m2 is 4, g of course is 9.8 meters per second squared. m1 is 1, and r is also 1 meter. And we find that omega is 6.26 radians per second, and a simple calculation can turn that into 60 revolutions per minute, correct to 3 significant figures. Now, worked example 6 has to do with banked corners, and you can see a couple of diagrams here. The one on the left is a picture showing the forces where the weight of, in this case, a NASCAR is the blue arrow W downwards. The normal force due to the banking of the curve, or the corner, is the green arrow and given capital N as the normal force. And the two of them, you can see on the right-hand side, a vector diagram shows that the sum of the vectors, the resultant force, is horizontal and, in this case, to the left. So here's the question. Pat is driving a NASCAR that has a mass of 1,500 kilograms. That's roughly, exactly, 1.5 tons. It's traveling horizontally at 80 kilometers per hour around a bend that is banked at 10 degrees to the horizontal. Part A, what is the net force acting on the car? And part B, what radius of curvature must the road have so that the car can turn the corner with no friction force acting downwards? Well, here's the first step. It's data. We know that theta equals 10 degrees. But where's the angle? We need to be careful identifying where the angle is in the vector diagram. We know the mass is 1,500 kilograms and the g is 9.8 meters per second squared. And we know that the velocity, the speed as it's going around the corner is 80 kilometers per hour. And we need to convert that to SI units by multiplying by 1,000, dividing by 60, dividing by 60 again, to get 22.2 meters per second. And here's the formula we're going to use, that the sum of the forces equals mg tan theta. Just show yourself in how that works with the vector diagram on the right hand side, with theta being the smaller of the two acute angles. The opposite then is the sum of the forces, the resultant force, and the adjacent is W, the weight, mg. And you should be able to see how this first line comes from basic trigonometry. And then we substitute 1,500 times 9.8 times tan 10 degrees. And we find that the sum of the forces, the resultant force towards the center, is 2,590 newtons, correct to 3 significant figures. For part B, and of course it's to the center, since F equals ma, then F also equals mv squared on r. But rearranging, putting r as the subject, because we want to find the radius of the curvature, r equals mv squared on F. And we've just found F. And we know the mass and we know the velocity. So we substitute 1,500 times 22.2 squared all over 2,590 will give us 285 meters, correct to 3 significant figures. So the radius of this curve is 285 meters. Now, worked example 7 deals with torque. Torque is force times the radial distance as it turns in a circle. So here's the question. Find the torque on the spanner when a 20 Newton force is applied at right angles 20 centimeters away from the pivot point. Our data is the distance, or the radius, perpendicular to the applied force is 0.2 meters using SI units, converting 20 centimeters to meters. The force, we're told, at right angles is 20 newtons, and we're required to find the torque. Now, the Greek letter tor is a small letter, and it looks a little bit like a T with a curly tail, and it's pronounced tor. And we use the formula tor equals r perpendicular f, which also equals rf sine theta. In this case, it's right angles, so sine of 90 degrees is 1, and we simply substitute 0.2 times 20 to get 4 Newton meters. And there's the man with the giant spanner applying a torque of 4 Newton meters. So those are straightforward calculations for circular motion. In the next video, there will be some more complicated calculations that are more like problems to be solved. I'm Mr. Mac. Thanks for watching.